Okay, so we have 36 people who joined us. So we'll start. Hello, everyone, and thank you for joining us on today's webinar. I'm Léo Ballon, a marketing manager at Cognitive Design Systems, and I'll be your moderator for this one-hour session. Before diving into the subject, please note that this session will be recorded and will be sent to all of you after the webinar. As you know, today is a very special day for us at CDS, as it is the first webinar on our brand new software Cognitive Design, so it's fantastic to see so many of you here. Cognitive design has been developed by our team to address key challenges faced by engineers when it comes to optimization and manufacturability in the design process. In this session, we'll mostly talk about design for manufacturability in additive manufacturing, as we observe that ensuring manufacturability for optimized or complex geometries can be quite daunting for engineers. Therefore, we'll demonstrate how cognitive design can help engineers overcome manufacturability issues through two case studies. First, we'll explore a complex topology-optimized design intended for mass production, demonstrating how cognitive design secures manufacturability from raw topology optimization results. Next, we'll look at a simpler industrial part that is currently produced through a conventional production method, highlighting how the software can help you effortlessly transition to additive manufacturing for more efficient production. By the end of this session, you will learn how to efficiently identify potential risks in the 3D printing process using cognitive design's analytical tools, how to make informed decisions based on the design analysis to ensure successful production, and will give you valuable insights into leveraging cognitive designs to tackle your next design challenges. I'm fortunate to have two experts with us today. First, Rushik Matroja, co-founder and CEO of Cognitive Design Systems, who will present the two different case studies of today and will guide us through a practical demo of cognitive design. Rushik, would you say some words?
Hello, everybody. It's fantastic to be here. I see also many familiar names in the list and excited to share more in detail. I am one of the co-founder and CEO of the company, and at CDS we help engineers transform concept into a high-performance, manufacturable, and profitable product through our software. And we will do the in-depth demo of it all together. Thank you very much for joining.
And then Théo Berthomieux, our product manager, will provide an overview of the software key capabilities, helping you understand its full value for your engineering needs. Théo, please.
Hello, everyone. Thank you for joining today. So as a product manager, today is a very special day for me since our product and its benefits are being showcased to all of you. So hope you will enjoy it.
Super. After their presentations, we'll open the floor to your questions, so please feel free to drop any question you have in the chat during the presentation. We'll address them during the Q&A at the end of the session. So, without further delay, let's get started. Théo, the stage is yours.
Thank you, Leo, for the full introduction. I'm delighted to be here today to introduce the advantage of our latest software solution, Cognitive Design. Before diving into its detail, let's look at some current engineering challenges that cognitive design address. So today, engineers often find themselves in a frustrating loop of redesign and adjustment to ensure that innovative design can actually be manufactured. In fact, adapting the design, to meet manufacturing constraints typically consume around 25% of a project budget. This issue is widespread. Approximately 40% of design are modified due to manufacturability challenges. And finally, more than half of design engineers report that this repetitive manual adjustment slow down the overall design process. As you can see, current challenges do impact on our productivity and are meant to be solved. So we were curious to see how and where bottlenecks in the engineering process could occur. To do so, we have analyzed along with our customer common engineering project and found the following. Right after the product specification on the timeline, and before the CAD design validation, we have the concept design phase. This step encapsulates from design to feasibility validation back and forth information transfer that can significantly delay project timelines. This not only impacts budget, but also stifles the creative potential that drives engineering innovation. A lack of agility caused by siloed technologies can reduce efficiency and limit the impact of your design. And that's where cognitive design steps in. This solution is tailored for engineers like you who want to accelerate design optimization and ensure that their designs are manufacturable. Here is how cognitive design achieves this through those three core values. The first one, centralized manufacturing knowledge. So access all relevant manufacturing expertise unified and available from the start of the design process. Secondly, informed and accelerated workflows. Your workflows are streamlined, keeping decision-making timely and in the loop. Finally, the third point, agility and flexibility. We empower an agile design process that supports optimization at every stage. So you might be thinking, why should I use cognitive design? What's in it for me? Let's go over some of the key benefits from design optimization to ensuring manufacturability. First, let's talk about performance. The simulation-driven design application within cognitive design optimize product design by integrated simulation data throughout the design process. The SDD app considers constraints such as the design space, functional region, mechanical parameters like maximum stress and pressure. By analyzing these inputs, it redistributes material to strengthen critical areas while removing it from unconstrained areas, ensuring efficient use of material. This approach supports real-time adjustment based on performance insights, making the design process faster, more efficient, and focused on the performance to achieve. Indeed, by adopting a SDD approach, you will be able to integrate simulation results early in the design process, make targeted geometry modification based on factors like stress and pressure, and finally iterate and fine-tune design quickly with our integrated implicit modeling engine. Then on the right side, the manufacturability. So the manufacturing-driven design application in cognitive design complements the simulation-driven design approach, making design interaction manufacturable. The MDD, as we call, prepares design for production by adapting them to specific manufacturing processes, addressing key risks like thickness variation, thermal concentration, and the printability of holes. With 5 targeted modifications, the MDD ensures that designs are optimized for manufacturability. So using this MDD approach, you can detect manufacturing risk related to part geometry using advanced analysis tool, automatically adjust geometry to ensure manufacturability, and maintain control over key geometric properties that are essential to your manufacturing processes. Now, I will let Roshik present the software itself.
Thank you, Theo, for this great introduction on cognitive design. Now, let's see it in detail and how it works. Let's start with the basics. Welcome to cognitive design. In the center, you have the canvas. On the left side, you have different components. On the top, in orange, you have applications, which are made out of various different components, which are just under. Applications will help you solve complex design problems in no time. Let's start with lightweighting. First of all, I imported a block called import vrep, where I selected my file. Once the file was selected, I connected it with Compute 3D model and clicked on Compute. Here you go. I have the 3D model visualization here. Now I will connect the visualization, so the 3D model, with the component called lightweighting, where I have two options. Either I can choose TPMS infill or lattice infill. In here, I have many different parameters, type of gyroids or other kind of TPMS that I want to use, various different thicknesses, the shell thickness, cell size, and based on this information, I'll be creating a lightweighted path. I made sure that I don't have any shell in this case, so we can visualize it pretty easily. And here you go. You have a part with the right cell size, with the very complex structures, which is lightweighted in no time. Imagine doing this in a CAD environment. This could be a very time-consuming process. Now let's go to our first case study. Our first case study is coming from aerospace industry, where we will be looking on at the door bracket of Falcon 6X from Dassault Aviation. The main challenge here was to convert a raw topology optimization result into a more functional, manufacturable design that is ready for production. For that purpose, we went to convert this component into this automatically and autonomously. Now imagine doing this in a CAD environment. It can be, you can have a lot of geometry operation troubles, you can lose topological features, and it can be a very time-consuming process overall. And time is money. How about if this process of converting a concept into a manufacturable part is automated and accelerated? The whole workflow is divided into four different parts. First of all, we will reconstruct the topology. Then we will find the suitable orientation of the path. And based on that orientation, thirdly, we will optimize for the manufacturability. And at the end, we will convert it back to CAD so we can bring it back in our conventional CAD environment to continue the work. So first of all, I import the raw topology optimization result. You can see here, it's a good looking part, but it's very thin. There are a lot of thin structures that are not easily manufacturable. I wanted to make it stiffer. For that, I imported also the design space. The design space I imported as a step file, which are shown in orange. And on the step file, I chose the functional regions in green. These functional regions are the regions that I want to keep as it is and have a minimum thickness that I want to specify. I connect everything in a component called topology optimization post process, where I import the design space, the functional region surfaces, and the raw topology optimization result. And I want to make sure that the functional regions have at least 3 millimeter of wall of thickness. The blend radius between the functional region and the remaining of the path is 1 millimeter to have a smooth transition. Then I have two different parameters to apply smoothing. We know that in some cases, topology optimization result will be very coarse. And the smoothing parameters will help you automatically smooth the part to make it usable. And then we have a wrapping strength. It's a unique feature in cognitive design where if somehow your functional region is disconnected from the remaining of topology, then you will be able to reconnect it based on the strength that you applied here. Let's see the result. The result looks pretty good. But we can see that there are some of the regions which are still very thin. Is it manufacturable? In order to do the assessment of manufacturability, first of all, we need to find what's the right way to produce this part. And in order to do that, we need to find the right orientation for this part. The orientation of the part will be done using our component called orientation. Simple. And we have many other components in term of manufacturing analysis, which are at the bottom of the list: orientation, nesting, surface roughness analysis, feature distortion, etc. We will see some of them today. Orientation component has many different parameters. So these parameters will allow you to choose how would you like to orient your part based on a functionality. So do you want to remove the support volume, or do you want to minimize the support volume, or do you want to maximize the surface contact of the part with the plate, or you want to maximize the number of parts on the plate, etc. Here in this scenario, as we wanted to go for a silk production, I want to minimize the support volume so I have less post-process, but on the same time, I wanted to make sure that the batch size is large enough so the cost can be reduced. That's why I chose 100 for these two parameters and 0 for the remaining. And it gave me one result which looks like this. It's an interesting result because it's a trade-off between the amount of support that is required and also the footprint of the part on the base plate that you are going to print with. So based on this result, I wanted to go ahead check the manufacturability. For that purpose, first of all, I choose feature distortion analysis. Feature distortion analysis allow me to set up a criteria that my minimum thickness that is allowed is 2 millimeter. So all the region where the minimum thickness is under 2 millimeter will be shown in red. And here we can see that there are some of the struts which are very thin, some connections here which are also very thin. So I wanted to make sure that this is this locally I can modify those regions. Now imagine doing this in a CAD environment. How much time will it take to convert those small features into acceptable thickness? A lot. But here we'll be using manufacturing-driven design. Manufacturing-driven design is an approach where we can take informed decision based on manufacturing analysis. In this case, we wanted to modify the thickness locally and bring all the thickness to at least 2 millimeter of criterion. And this was possible to do in just a few seconds. Incredible, right? So this is something that is pretty easy to do in cognitive design. And on the same time, you can always validate with manufacturing analysis, which is integrated into the software. So you make sure that, okay, all your features are manufacturable. Now I wanted to check the support structures. For that, we have another component called support estimation, where I was able to estimate the support required at a different part of a different region of the part. In red, these are the supports which are from part to part, and in blue, supports are from part to plate. We can see that there is a lot of supports inside the hole, and I wanted to change that. I wanted to make a diamond shape there so I don't have to create support structures, and on the same time I can reduce I will be able to do easily machining on top of it to create the cylinder once again in the right acceptable criteria. For that, I choose the cylinders that I want to modify. I import them together with the path, and this time I will be using hole printability strategy. As you can see in manufacturing driven design, we have multiple strategies. We just saw before thickness offset, then we saw thickness ribbing, then we will see thickness ribbing in the second use case. We can also alleviate the thermal concentration by modifying it by hollowing the part and creating a self-supporting structures. We call it smart hollowing. You can modify the hole printability or you can even create the holes for powder removal pretty easily. Here in this case, I wanted to modify the holes and make them diamond. So there you go. In few seconds, you have the diamond holes which are generated pretty autonomously. And you can always validate it using once again support estimation feature and see that, okay, there are less supports inside the holes. So it's a better approach. At the end, I wanted to make sure that the part is a viable solution. So I wanted to bring it back to CAD environment so I can modify if it's required. And for that purpose, I used FREP to BREP functionality, where I created a quad mesh on top of it. And this quad mesh allowed me to generate a step file pretty easily. And this part, I can export it as a .step file pretty easily. So this is our first application where the whole workflow from raw topology optimization to CAD part was set up in about 20 minutes of time. And it takes approximately 5 minutes to run the whole end-to-end workflow. Something which is unimaginable in CAD environment. While doing this, we also ensure the manufacturability of the part, which is the key component and unique value that we are bringing to the industry. Now let's go to the second use case. The next application is coming from automotive sports industry. The part itself is a bell housing of LMP1 car, which was designed by Perrin. So it's a Perrin LMP1 sports car. The whole idea behind this part was to reduce the weight of the part and have a shorter lead time. In order to do that, we need to change the manufacturing process from sandcasting to additive manufacturing. And the main challenge was that when we have an optimized design that was done using simulation-driven design that I mentioned just after, we wanted to make sure that it's also manufacturable using powder bed fusion technology and in additive manufacturing process. So to start with, what we did is the original part, which was weighing 9.5 kilogram, also made in sandcasting process. We did some simulation-driven design on top of it. So we took the simulation result. We saw where the stress was high and the stress was low. Where the stress was high, we kept the part itself, so the thickness of the part as it is. And where the stress was low, we removed some of the thickness. So we created lightweighting using variable offset. It's a negative variable offset. By doing that, we were able to reduce more than 20% in terms of weight. But when we checked for manufacturability, we found out that there are a lot of manufacturing risks which were detected. And in order to alleviate the manufacturing risk, we applied manufacturing-driven design, which increased the weight a little bit, but we were still able to have 13% of weight reduction while ensuring the manufacturability of the part. Let's check out the workflow itself. First of all, I imported the part itself and ran a quick feature distortion analysis, and we found out that okay, there are a lot of zones which are in red. So what I wanted to do is that I wanted to add some ribs at the surfaces which are in red, and don't add the ribs where it is good. So we used thickness ribbing strategy in manufacturing-driven design, and it gave us a pretty good-looking part with the ribs where it's required only, and this was done pretty fast and automatically. We can't imagine to do such operation in a CAD environment, because of the complexity of the surfaces, but also because of because of the complexity of geometry operations that it requires. Once I had the ribs in place, I did a whole printability optimization, and I was able to convert those holes into diamond also in pretty quickly. You can imagine that there are like plenty of holes. There are a lot of holes everywhere in each direction. We wanted to make sure that only the holes which are in which has the axis in Z in the plane XY are modified, and the holes which has axis in Z direction are kept as it is because it doesn't require any supports there. So these holes are left as it is, and the holes on the side were changed to make it manufacturable without support. Once the modification is done, I went through another feature distortion analysis, and the part was looking pretty good. And this is something that I can export pretty easily. Now I'm going back to the slides and go to the conclusion of the presentation. We went through two different use cases, one from aerospace industry and another from automotive sports industry, where we were able to do the reconstruction of topology optimization result to make the part manufacturable based on identifying the manufacturing risk and applying the modification. It's a perfect example of informed design decisions. Secondly, we were able to convert those geometries into CAD, so we can reuse them in a conventional CAD environment. We were able to also, in second use case, in the bell housing, incorporate simulation-driven design, where we modified the design of the part using stress as our information, and once again doing informed design decisions to alleviate the weight. We also did iterations to fine-tune the design at very high speed, and everything was done semi-autonomously, which allowed us to gain time in the whole design cycle. I'll pass on to my colleague Theo to continue the discussion on other topics. Thank you.
Thank you, Rashik, for the great in-depth demonstration of cognitive design capabilities. So now let's discuss how you can start using cognitive design. So we are excited to offer a launch price package, cognitive design with all features, apps, and meshless FEA simulation is available for €375 per month until the end of the year. Additionally, some of you have already joined our special 60-day free trial campaign, which is still open until Formnext. Don't miss this last opportunity. Please scan the QR code to apply.
I think you're on mute.
Oh, sorry, guys. Sorry. So thank you, Theo, for all these informations about cognitive design's offer. So now, guys, we are moving into the Q&A session. So if you have any questions, feel free to drop them in the chat. We'll do our best to answer as many as possible. So now let's get into the questions. So I see a first question here. Can we do MDD on complex structures such as lattices? Rashik, Theo?
Yeah, so definitely. I mean, we use a very powerful geometry engine, which is based on mesh, implicit, and BREF functionalities. And you can definitely do manufacturing-driven design analysis and optimization on top of lattice structures or any other complex structures.
Okay. Another here, what type of format can we export from your workflow? STL only or step as well?
I'll take this question. So cognitive design can export STL file and step file. So exactly what Rashik could show during the presentation, you can export a step file.
Okay. Another question, can I do more modifications to the exported step file in CAD?
So yes, we can, because it's a step file, so you can directly in any CAD software like CATIA or Autodesk Fusion do modifications.
Okay. And another, is simulation-driven design better than topology optimization?
Yeah, so I will answer this one. Simulation-driven design and topology optimization are two different way of lightweighting the path. Both have their advantage and disadvantage. Simulation-driven design is more an engineering approach where you are in control of all the geometry modifications you can do, and both have its own advantage in the depending on the use case. So I would say that there is no better or worse. It depends on the use case.
Okay. Is optimization possible based on casting processes?
Yeah. So currently the optimization is based the optimization that we are doing it is on additive manufacturing process, and very soon we will have also possibility to do the manufacturing driven design based on machining, die casting, injection molding, and forging processes.
Okay, we have a question from Bastian here. How about turning, milling, restriction?
So it's the same
Same, yeah.
answer as before.
Okay.
These are the processes that will be added in coming months in our software. So you will have multi-process optimization possible. That would be a real advantage for the users. I really understand.
Yeah.
Okay. A question again from Bastian. Can you create optimization inside of this software, or is it only post-processing?
So the simulation-driven design optimization that we are doing is definitely you can do it inside the software. You will be able to simulate your part, and based on the simulation result, you will be able to drive your geometry to better manage the material distribution, and in this way you will be doing the weight reduction optimization.
Okay, thank you. Miguel is asking, is there any way to define constrained fixed surfaces for optimization directly into the application?
Yes, definitely. You can define which orientation you want to do. Either you can use our component called orientation to define the direction of printing. You can also select surfaces that you want to keep as it is, functional regions, I believe, and this will be taken care in manufacturing-driven design and simulation-driven design, both of them.
Okay, now we have a question from Ivan about the licensing. Is it possible to have the software with a floating license?
I will take this question. So not at this moment, but we can discuss together after the meeting to see if there are any solution for that. Yeah. but it's not available at this moment.
Our current licensing process is based on the PC. So you will the license will be connected with your local PC, and that's how it works for the moment.
It's on-premise software, so that's why it's locked to the computer at this moment.
Okay. Another question here, how does manufactured part compare to the simulation? Any further optimization loops required?
Sorry, can you repeat one more time the question?
How does manufactured part compare to the simulation? Any further optimization loops required?
So definitely, I mean, this is the real advantage of the software. You can do the loop between the simulation and the manufacturing analysis and the optimization of both, and you can fine tune the parameters to achieve the best performance out of your part, but also the best manufacturability of the part also.
Okay. And another question from Yunus. Is the part expressed as ready to print, prepared automatically, or did you manually adjust? Is it possible to make manual adjustments?
So currently, the part which is that we get out of it, it's something which is highly printable, of course, because we applied the manufacturing driven design. If you want to apply a manual adjustment, it would depend on what kind of adjustment you want to do, because it's a quite broad question. But there will be possibility of doing smoothing. You will be able to also do some other geometry operations if it's required.
Okay. Another question from René. Is the outer ribs design able to follow a weight percentage requirements?
Great question, René. So this is a very interesting topic. Currently, the ribs that we are generating, it's based on the parameter. And we are working on creating a parametric optimization to achieve the weight target or weight reduction target. This is something which will be coming up in the software, but the software is ready to host such kind of optimization.
Okay. So again, a question about the loops. For the subsequent loops, can you feed the software with the 3D measurement of the prototype manufactured?
No, we don't have that capability at the moment in the software. Thank you for asking. I will look into it.
Okay, guys. So I think we are good with the questions. Sorry for those who asked the questions, but we couldn't really answer. The time is running. So thank you all. As the webinar gets to its end, I would like to mention that for those who want to dive deeper into cognitive design's capabilities, we'll be exhibiting at Formnext this year. So as you know, Formnext is a fantastic opportunity to meet with you in person. So please drop by our booth next week to connect with the team and explore even more our solutions firsthand. If you are interested in trying cognitive design for yourself, of course, don't forget to scan the QR code on your screen to start a 60-day free trial. And as I mentioned at the beginning of the webinar, a recording will be sent to all of you via email at the end of the session. So, behalf on the whole CDS team, thank you all for joining us today. We wish you all the best in your upcoming engineering project. Take care and goodbye.